Hi ladies and gentlemen, let me welcome you to the 26th session of ECT 204 Signals and Systems. So in this video we employ Laplace Transforms to analyze continuous time LTI systems. The contents of today's session are your learning outcomes, then LTI system in S domain, causal LTI systems, stability in the S domain, then the summary of understanding. Then in this video you will learn to employ Laplace transforms to analyze LTI systems. The input-output relation of a continuous time LTI system is a yt that is equal to xt convolution ht. So applying Laplace transform on either side, ys equal to xs into hs. So you know this is because of the convolution theorem, because a time domain convolution is equal to a frequency domain multiplication. So the frequency response hs that is equal to ys by xs. Now let us use this method to compute the output of an LTI system whose impulse response is e raised to minus 2t ut, that is driven by the signal xt equal to e raised to minus 3t ut. So hs is 1 by s plus 2 because hs is 1 by s plus 2 because ht is e raised to minus 2t ut. You know that a signal e raised to minus 3 alpha t ut has a transform of 1 by s plus alpha. So here hs is 1 by s plus 2 and x of s is 1 by s plus 3. So ys is hs into xs, so that is 1 by s plus 2 into s plus 3. So by taking by putting this into partial fractions, so for putting into partial fractions I have to know the residues of each s plus 2 and s plus 3. So s plus 2 has a pole s equal to minus 2. So corresponding residue is 1 by minus 2 plus 3, that's a 1. That is, how do I compute that residue? I put s equal to minus 2 in this equation by masking this s plus 2, that is equivalent to a multiplication by s plus 2. So the first residue is 1 by minus 2 plus 3, that's a 1. And here s equal to minus 3 is a pole, that is 1 by minus 3 plus 2, that's equal to minus 1. So it is a 1 by s plus 2 minus 1 by s plus 3. So that output yt is e raised to minus 2t ut minus e raised to minus 3t ut. If I have an LTI system ht equal to e raised to minus 2t ut, that is driven by the input signal xt equal to ut, so what is the output? So hs is 1 by s plus 2. This is e raised to minus 2t ut, so it is the transform is 1 by s plus 2. The second signal xt is ut, so xs is 1 by s, so output ys equal to xs into hs. I see a small mistake. So the output is ys is hs into xs, that is 1 by s into s plus 2. So by the earlier method of partial fractions, what is the residue for s equal to 0 is a pole for the first function. So when I put s equal to 0 in 1 by s into s plus 2 by masking this s, it becomes 1 by 0 plus 2, that's a half. So the residue for the first time is half, the numerator for the first time is half, and for the second one the pole is minus 2. So here the residue will be 1 by minus 2, that's a minus 1 by 2. So what is the output? Yt is half of ut minus half of e raised to minus 2t ut. Now let us use Laplace transforms to understand causal system. So the condition of causality is that ht equal to 0 for an LTI system, ht equal to 0 for t less than 0. So ht should be a fully right-sided signal. So the ROC of h should be h of s should be in the region where real part of s is the sigma max, where sigma max is the maximum real part of any of the poles of hs. So hs will have many poles in there, like say 1 by s, or it is 1 by s plus s minus 2, something like that. So look at the maximum pole, maximum value of the pole, let that be a sigma max. Sigma max is a maximum real part of any of the poles of hs. So the condition for the causality is that real part of s should be greater than sigma max. That is something like this. This is a causal system. This is the maximum value of the pole that is available in HS. So from here to the right, if the if your region of convergence, if that is to the right of this thing, then this is a causal system. Suppose this is the one, suppose and the condition for non-causality, that is real part of S is less than sigma min. Sigma min is a minimum real part of any pole. That is, if this this is sigma min and this is the region of convergence, then it's an anti-causal system. So it should be known that HT should be a right-sided signal. That is, the ROC of HS is a right half of the S plane. That is the right side of some maximum pole sigma max. Now let us look at the stability in the S domain. For a continuous time LTI system to be stable, it should be this HT should be absolutely integrable. That is, minus infinity to infinity integral mod HT dt should be less than infinity. So HS is equal to minus infinity to infinity HT raised to minus ST dt. And assuming that S equal to sigma is equal to j omega, S equal to j omega, mod H j omega becomes mod of minus infinity to infinity integral HT raised to minus j omega t dt mod. Okay. That is less than or equal to minus infinity to infinity. I interchange the summation and the modulus sign. So this modulus of the sum is less than the sum of the modulus. Okay, because these are all absolute values. When I integrate, they are all positive. So that tends to be a larger value than the modulus of the integral. So this value is less than or equal to minus infinity to infinity integral mod HT raised to minus j omega t dt. And you know that modulus of e raised to minus j omega t is always 1. So this value is less than or equal to, this mod h j omega is less than or equal to minus infinity to infinity mod HT dt. Okay. It means that here we have this assumption. So this is the condition for my stability. So how did I reach that condition? Assuming that S equal to j omega. That means for a stable system, the ROC of HS should contain the imaginary axis. So whatever ROC of HS, that should contain the imaginary axis. So this right side, this stable system, because the imaginary axis is contained in the ROC. This is an unstable system because the ROC does not contain the my imaginary axis. Okay, ROC does not contain the imaginary axis. So if it is a stable system, the region of convergence should contain the imaginary axis. Now, if a system is causal and stable, then all poles must lie on the negative S plane. That is, all poles have negative real parts. Since ROC is a form, real part of S greater than sigma max, and the j omega axis is contained in the ROC. Because if it is both causal and stable, then all poles must lie on the negative S plane. Okay, all poles should be on the negative S plane, because it is from the poles that your ROC starts, and ROC should contain the imaginary axis. So all poles, if it is a causal and stable system, then all poles of HS should lie on the negative half of the S plane. Now, when you come to the summary of understanding, in this video we learned to analyze LTI systems with the Laplace transforms and understood stability and causality with the help of the S domain. And that is the end of this presentation. I thank you all.